it's time to start the next talk. So it's my pleasure to introduce Nikolay Malkin from the University of Edinburgh, a colleague of mine. We're in the same school. So he's going to talk about diffusion models, give an introduction to them before then giving later this week also a research talk on the related topic. The floor is yours.
Yes, thank you for the invitation. I should say in November I gave a short mini course, 4 hours on diffusion models, and I think that's the reason that I was asked to give a condensed version here for 1 hour. Now it will be a little different than it was this morning because I will not talk about my own work. I will talk about diffusion models as they existed in the literature maybe a couple of years ago. Diffusion models are a kind of deep generative model, or I should say a kind of parametric generative process together with the training algorithms for it. And they're trained given a data set to eventually generate samples which mimic that data set. So we'll talk about that today, and in my talk on Wednesday, and in some other talks later in the workshop, we'll hear about other uses where we train diffusion models without data as inference edges. So with that, let's begin. But just keep in mind, maybe little less maths, more pictures of cats. That's the way it is. Right. So diffusion models are used for all modalities of data. They're not tied to any particular space, any particular neural net architecture, and so on. So they're commonly used to generate, say, pictures given a caption. That's a very realistic picture of Edinburgh from a hill in the city, although there's one steeple hallucinated in the middle of the castle. Lately, they're used for trajectory planning, say in robotics, combinatorial optimization. Here, a diffusion model solves a traveling salesman. This is actually from the first work I ever published in diffusion. And 3D structures and biological and chemical design. Diffusion models were used for protein folding, which led to the 2024 Nobel Prize in Chemistry, as some of you might know. So in presentation about diffusion, I often like to show this tweet I saw. They really are everywhere, and their presence is only growing. So in this tutorial, I want to tell you what a diffusion model is, what's related to, and there are many such things. The main point of view will be that a diffusion model is a kind of deep latent variable model, or deep hierarchical variational autoencoder. But it's also a few other things in disguise. It's a score-based model, so a model that approximates the gradient of the log density of the distribution convolved with a certain level of Gaussian noise. It's also a continuous time process and related to the theory of continuous time Markov chains in dynamical systems. Now, we probably won't get to all of these things in detail, but it's just important to realize all these connections exist, and somehow there's a fruitful transfer of ideas and algorithms between these 3 points of view. And in the other talks, we'll hear some other points of view, like diffusion models are actually RL agents or amortized samplers. So here's the plan of what we'll do today. Just short historical overview, then the latent variable model view of diffusion, then 2 important connections related to that. So what diffusion has to do with denoising, as diffusion models are commonly understood, and what it has to do with score matching. Then we'll talk about conditioning and guidance in diffusion models, which is important in many of their uses. And then, if there's time, continuous time perspective, and then we'll conclude. All right, so historical overview. Well, the diffusion models appeared in some form in literature a very long time ago, maybe since Poisson wrote down the heat equation 200 years ago. But at least since they appeared in their modern, something close to their modern form 30 years ago, the principles haven't changed much. So to generate samples from an approximation to a distribution, we start with random noise, and we gradually transform this Gaussian noise by stochastic steps until it comes to resemble samples from the distribution that we like. So lots of local steps, eventually get samples, that's all. So perhaps the first... Okay. No. The ability to advance slides would be very helpful now. I apologize, the arrow key doesn't work, clicker doesn't work. I'm really at a loss. There, okay, there we go. I had to exit full screen and do that again. Sorry about this. Back to full screen. Perhaps the first work that talked about diffusion models in a form close to how we're thought of now is from 1993. This paper is really fun. It's by psychologists or cognitive scientists, and they talk about how when the brain decides what action to take, say whether to follow this road to the left or to the right, it has to model the multimodal distribution. Because if you just regress to the mean, you'll end up going straight into the between the two rows. And if we gradually resolve our neural activations by steady steps, we can model multimodal distributions. So sometimes end up on the left, sometimes on the right, but not the average. Now, here the behavior of a single neuron was modeled, hardly high-dimensional, and not even very multimodal. But this motivated diffusion models before modern deep learning existed. There was a gap for some time. There was this work in 2015, which was inspired by non-equilibrium thermodynamics, and first introduced diffusion models in basically the current form. But the deep learning techniques were not quite there yet, and so the images generated when these things were trained on small image datasets were not really realistic. After that, there are steady improvements. This is probably the most cited paper on diffusion models, and we have images, the CIFAR10 dataset, which actually look like a recognizable class, and then steadily these were scaled up through various learning and neural net architecture and other techniques. And this progress has continued to the present day with new modalities, better training algorithms, and scaling all gradually improving. And by this point, diffusion models are the state-of-the-art family of generative models well, for images, but also on a wide variety of other things. So what is a diffusion model then? So quick review first of I'm really sorry. I think I've understood what's going on with Adobe. I have updated the file, and it opens a file which is not the current version, because I've removed one word from this slide, and now I see it here. But I think this should be fine. Anyway, let's continue. So, latent variable models. All right, this is probably very familiar to everyone. So, in latent variable model, we have observed data, x. We have latent variables, z. To generate samples, we can do so ancestrally. So we sample the latent variable z from some prior distribution, and then we generate our samples conditioned on the latent variable. And so many models in machine learning, both in deep learning and classically, have this form. So it can be a mixture, index, a topic vector, whatever you like. So both the prior and the conditional distribution may depend on some learned parameters, say if they're neural nets of some form. And then the likelihood of a given sample x under this model is given by marginalizing out the latent. Now, this marginalization itself might be intractable, which is an important challenge for both training and evaluation of such models. But sampling is easy. So, both in training and to perform statistical inference, we were interested in getting the posterior distribution over the latent, given some data observation. And this posterior may be intractable for general forms of the model, and we often want to approximate it through amortization or sampling techniques. Right, so we can think of latent variable models, the posterior in a latent variable model as an encoder, so it gives us a hidden representation of the observed data. So for example, in an autoencoder, a variational autoencoder, the samples are represented in latent space in a way that meaningfully preserves some semantic information. Say here's a data set of digits, I fit a model with two-dimensional latent on it, and you can see that the colors correspond to digit classes, so meaningfully clustered. Right. And 2D data set, same thing. So how do we train such models? So when we do maximum likelihood training of generative models, we have a data set where we assume independence of samples, so we want to maximize the total log likelihood with respect to the parameters of both the prior and the conditional generative distribution. Now the problem is that this involves this intractable integral over the latent, so we can't optimize it directly. So to get around this problem, we introduce a variational distribution, which is supposed to be approximating the posterior. So we have the Gibbs inequality, form of Jensen's, which says that for any posterior distribution over the latent given the data, the log likelihood is lower bounded by this expression, which averages the log likelihood over the variational posterior. And this inequality becomes an equality if this approximate variational posterior Q becomes equal to the true one. And in order to maximize the log likelihood of the data under the model, we instead maximize this lower bound, called the evidence lower bound, or you may know it as the negative of the variational free energy. So we have to optimize this thing, and we can do it with respect to both Q, the approximate posterior, and P, the generative model. So this leads to the EM algorithm, expectation maximization. We have that expression, the elbow, which we aim to maximize. So we approximate Q with a model, or we store it as a table if the model is simple enough. And we train Q to approximate the posterior in some way. And that's the E step, expectation. And in the maximization step, we need to optimize with respect to P. And to do that, all we have to do is sample the latent from a posterior and take gradient steps on the log likelihood under the model P. If the posterior model happens to be fixed, which seems a little strange, but we'll see meaningful examples soon, then it's very simple. We just have to take our X, sample Z from the fixed Q, posterior, and make gradient steps on the log likelihood under the model. Now, this can also be made hierarchical. We can have a sequence of latent variables. Don't worry, there will be examples very soon. So if we have a sequence of latent variables forming a Markov chain, so with this graphical model structure with conditional distributions saying how to transition from each latent variable to the next, and the last one is observed, we do the same thing. We need to maximize log likelihood. We introduce approximate posteriors going in the other directions. We factorize this distribution right to left instead, and optimize this hierarchical evidence lower bound in exactly the same way. So the fixed posterior model Q, we take X, sample the chain of latents right to left, and maximize log likelihood in the left-right factorization. Okay, so now diffusion models are just models like that with a very particular form of Q. So we identify X with, for simplicity of notation, with the latent variable Z0. And the posterior model Q is going to be like this. To go from Qn to Qn plus 1, we add a small amount of Gaussian noise to Zn. Now, I am lying to you just a little. Sometimes you also do a linear scaling in addition to adding Gaussian noise, but just for simplicity, we'll stick to this, and everything else is equivalent by just making a change of variables. So our right to left model, our Q, is just addition of Gaussian noise in every step, independent Gaussian noises. Now, if that's a posterior, what does training the model do? It means learning to reverse the addition of small Gaussian noises, going left to right. So let's look at this 2D dataset. So the 2D dataset consists of the points on the cat. So I've taken right there some points on the cat, and to each point I've added a Gaussian noise to pass to the previous panel. And I've done this for 10 steps. And the colored points are just some individual distinguished points so you can track how they move. And as you add a large amount of Gaussian noise, the signal is almost completely lost. So there's very close to zero mutual information between Z0 and Z9. And in fact, Z9 is approximately Gaussian because the total amount of noise I've added is much larger than the variance of the original cat. I've just scaled the picture to make it make it all fit consistent. So how do we train then? Well, we take a data point x, we sample our Q, so we sample our sequence of noisier and noisier points, and then we take a gradient step on the likelihood of following that same chain in the reverse direction, that's P. And we repeat the gradient steps on many, many data samples, and eventually we get our model. So this leaves open the question of how to actually model this step backward under P from Zn to Zn minus 1. Usually it's also modeled as Gaussian, usually with fixed variance, and you only learn the mean. And its variance is somehow related to the noise added in the other direction. So these assumptions can be relaxed in certain cases, especially with non-Euclidean data, but let's assume our transitions in both directions are Gaussian. So what do we do then? So here's the model I showed before. It's fixed. We start with the points on the cat. We gradually add noise until we get to just almost pure Gaussian noise. Now I fit a model. I really fit a model. It's a very, very small neural net. Now I can start with points which are just random Gaussian noise, and then evaluate the model, which computes for me the mean, the conditional mean of the Gaussian. So given this point, I try to this point, and to this point, and so on. Sample then Z8 given Z9, Z7 given Z8, and so on, until I get Z0, which you can see is distributed approximately like the cat, but it's quite noisy because my model isn't fit perfectly. But if I had fit perfectly and done many steps, then I would recover exactly the original data distribution, the original data set. So that's all. That's really all a diffusion model is. Now, there are of course many more connections and things to be said. So let's go there. Now, I showed you a 2D cat, but diffusion models are used to generate images. And if you tried to generate images the same way that I trained that model with a 2D cat, it wouldn't really work. And it wouldn't work for several reasons. The first one is that generating real pictures of cats with this Gaussian transitions Zn given Zn minus 1 would require hundreds of steps. At least if the transitions are Gaussian. There is work where, for example, a generative adversarial network is trained for Zn minus 1 given Zn, and then you can get away with 10 steps, or even fewer. But anyway, you need many, many steps to get a good approximation to a very non-smooth target distribution. But there are other reasons. But before that, a few observations on the model we've seen so far. So, first of all, as I've already noted, if we add a total Gaussian noise to initial samples x, whose variance is much greater than that of the data distribution, then the final noise latent becomes very close to Gaussian. So that first prior distribution P of Zn, the highest level latent, is usually fixed to Gaussian. Second, an important choice is the rate at which we add noise when we make a fixed number of steps. So in the picture, there were 9 steps of addition of noise, but I had to choose how much Gaussian noise was added at every step. And in practice, that can be an important design choice. Another observation is when we're maximizing this log likelihood, we don't have to actually write out the whole chain of latents and maximize the whole thing's log likelihood. We can just sample one term in this and optimize it. And this is good for parallel computation and computational efficiency. Now, there are 2 magic properties which I did not show you in the 2D cat, but without which large-scale training of diffusion models would not work. So the first thing is that we can do simulation-free training. So what does this mean? This means that, so let's say I have x, which is Z0, and I want to get the noisy latent, say, Z7. I don't actually need to sample the whole chain up to Z7, because if I add many independent Gaussian noises, it's the same as adding one big Gaussian noise with the total variance. So I can simulate, I can get Zn minus 1, Zn without going through all the intermediate steps. So no simulation of the Q in order to get a single term, one of these terms in the loss. Now the second property is that, well, in this In this objective, we're trying to predict, we're trying to model the parameters of a distribution which transitions from Zn to Zn minus 1. But in fact, there is some simplification possible, which I'll show you in a second, which allows you to not have to learn to go back one step to slightly less noisy data, but to go back all the way to the noiseless data X. And this enables a much lower variance training objective. And without that, it would be impossible to fit diffusion models on a large scale. So that comes next. In different generalizations of diffusion models, especially to non-Euclidean spaces and so on, you lose these properties. And sometimes other techniques are needed to make training efficient. Before we go to those little bit of algebra, why did we take this latent variable model perspective and not others? Well, if we think of diffusion models this way, as just deep hierarchical latent variable models, we easily get generalizations. For example, latent diffusion, in which the data X is first encoded into a latent space, lower dimensional latent space, and all the diffusion, all of the chain of addition of Gaussian noise happens in latent space. That's how most large-scale image generative models work. So here's the architecture of one called stable diffusion, which you may have heard, play with online. So we have a pixel space encoded into the latent space, then some unit and transformer magic in the middle, and then decode and get back an image. So then you can generate pictures like this. This is, I think, 2048 pixels across. If you try to work directly in pixel space, just adding Gaussian noise to each of the millions of pixels in this image, it would just be computationally impossible. So we can easily just do everything in latent space and include an extra step which passes this stochastic map between latent and observation space. Another reason is that it's easy to generalize to non-Gaussian noises. For example, interpolating between two data distributions, cats to lions, who knows. Or, as in this work, general noising processes such as blurring, pixelation, adding masks, and other image transformations. So with this view, nobody forces us to stick to addition of independent Gaussian noises. We can think much more generally. All right, so now let's do a little bit of algebra, and I'll show you these two magic properties and a connection to square magic. So recall that we were looking at this latent variable model in which we have a fixed model Q, which begins with x equals at 0, and gradually adds Gaussian noises to transition right to left. And we're fitting a model which predicts the means of the Gaussian transitions that go left to right, and thus ultimately generate through a sequence of steps the sample x. So given z0, zn is conditionally Gaussian, and its mean is z0, and its variance is the sum of the variances of noises we added per step. So let's just abbreviate this. Called Vn is this total variance, the sum of sigma squareds, variances per step. The training procedure was what? So we sample x from dataset, we go to some time step n, we follow q and noise x up to latent number n, and then we maximize the log likelihood of passing to Zn-1 from Zn. So if we model this transition as Gaussian, then we're trying to predict this mean. And of course, doing maximum likelihood training of a Gaussian mean parameter is the same as regressing to the value whose likelihood we're trying to maximize. So we're regressing to the conditional expectation of Zn-1 given Zn. So fitting the denoiser, the thing that passes from each latent to the next latent, is the same as regressing to a conditional mean. Now, what's this conditional mean then? Just on the picture. So let's say we have a data set of 2 points, and here are noisy versions of those points. Noisy and then slightly noisier. So we have, given the this point we have these samples, this point we have these samples. So the conditional expectation might look something like this. Given Zn could have come from this Zn minus 1, or any of these really. But some of those may have come from the blue point, and some from the it doesn't look red on the screen, it looks red on my screen. And comes some from the red point. So let's break up this expectation. So the expectation over Zn given Zn minus 1 given Zn can be broken up into an expectation over Z0. Now, because of basic Gaussian knots, this simplifies. Just some algebra with a narrative expectation, and we get this expression. So the mean of Zn minus 1 given Zn is actually a weighted average of Zn itself, and the conditional expectation of Z0, the noiseless data, given Zn. So this means, so the Vn's are fixed, the sigma n's are fixed. So this tells us that to estimate the conditional mean for one step slightly less noisy, we really just need to estimate the conditional expectation of Z0, the completely noiseless sample, given the noisy latent Zn. So just on a picture, so that picture I showed you before, this Zn could have come from a blue Zn minus 1 or a red Zn minus 1. This conditional expectation is a weighted average of this conditional expectation, given that it came from the red point, and this one, given that it came from the blue point. And the conditional expectation we're trying to estimate, which is right here, where the thick black arrow crosses this line, is just a linear combination of Zn and the conditional mean of the conditional expectation of Z0 given Z. Right, so the takeaway is we just need to estimate the expected Z0 given Zn. And that's easy to do. We get the simplified training algorithm. So rather than sampling a chain of latents and maximizing the stepwise log likelihood, we can just do this. Sample Z0 from the dataset, sample Zn by adding the right amount of total noise, and then just regress to the original Z0. So if I do that, then the model I fit optimally will be estimating that conditional expectation, and from it, the conditional expectation of Zn minus 1 given Zn can be recovered just algebraically by the previous slide. So it's a stochastic regression. Each Zn that I see, say this one, could have come from many different Z0s. But the probability it came from a given Z0 is proportional to the likelihood that that Z0 would have been noise to Zn. Bayes rule. So the result of this stochastic regression is something from which I can recover a predictor of Zn minus 1 given Zn. Now, there's some practical considerations. Often for models, there are inductive biases you put. For example, you may predict not Z0, but Zn minus Z0, or predict the noise like in the reparameterization trick, or other things of this sort. But those are really details. Anyway, we have an all-the-way denoiser from which one-step denoiser can be recovered. That's the magic property. This is so because we have a fixed training distribution, and we're just regressing to the original data sample. This means this makes training of diffusion models very stable and enables us to scale to very high dimensions and large models. Now let's catch another connection. This time is score matching. So I personally believe this to be the biggest, the most important algebraic identity in what should I say, in latent variable modeling. So it says this. Let's say I have a mixture model, and what's the gradient of the log likelihood of a mixture model? It's actually it's a convex combination of the gradients of the log likelihoods of the components weighted by the posterior. And this actually comes up all the time, and it's the principle behind EM. So let's see what this gives us. It gives a very nice fact in the case of diffusion models. So if Z0 comes from a data set, and Zn is Z0 plus Gaussian noise, then Zn follows a Gaussian mixture model, whose means are the points of the data set, and all the variances are just the variance of the noise that we added. So P of Zn, so we'll call it Pn of Zn, is a mixture model centered on the dataset with given variance for each component. So what's the gradient of log likelihood of that thing? So the Stein score, if you like, gradient with respect to Z of the log density. Well, we do some algebra, so this is gradient of log is written like this. And then here we have our magical identity. The score of the mixture is the weighted combination of scores of components weighted by the posterior that a given Zn came from Z0. Or, doing some more algebra, this is expectation over Z0 given Zn, the posterior. I see a noisy data point, which point of the data set did it come from? And I take the expectation of the score of the Gaussian distribution centered on Z0. So then just by algebra, this simplifies to an expression which involves just the expectation of Z0 given Zn. So what do we have from all this? The score of the marginal density of Zn is expressed in terms of the conditional expectation of Z0 given Zn. That should look familiar. So recall that this Z0 given Zn is what we're predicting when we're training our model P. So the result of training is not just a one-step denoiser, it's also the score function. So what have we shown? So we showed that the conditional expectation of going one step from Zn to Z-1 is expressed in terms of this denoiser, expected noiseless data given noisy data. And we've shown similarly that the score of the marginal distribution is expressed in terms of the same. So these three objects are all related to each other by just affine transformations where we know all the coefficients. So learning to denoise a single step passed from Zn to Z-1 is the same as learning to denoise all the way, and it's the same as just learning the score function of the noised data distribution. These are all just algebraically the same thing. So that makes different ways of thinking about the same generative model connected. So diffusion models are denoising autoencoders, if you like. The encoder just adds noise, and the denoiser goes back and tries to recover the data. And there are also score matching models. Score matching models are those which approximate the score function of the data distribution. Just these score matching models are working at many different levels of Gaussian noise added to the original distribution. This connection becomes important in the continuous time limit, which we'll mention closer to the end. But we're actually doing quite well on time. Okay, let's look again at our cat example. So I've got here the points of the cat. Now this is a data set. It's a sum of delta functions. I obviously can't compute the score function unless I go to generalized functions. So I've shown here a plot of the density of this distribution convolved with different levels of Gaussian noise. And as you can see, it approaches just a Gaussian blob at the end. And here at the bottom panel, I've shown samples from all those noisy distributions. The score functions look something like this. So at the low noise levels, the score is just pointing, well, the score is always pointing up the gradient of log likelihood. It's pointing toward the nearest data sample. So here it's just pointing toward the nearest data sample. As we go to higher levels of noise, in the middle ranges, what will happen is if you take like a low-dimensional manifold approximation to the data, it'll be doing approximately orthogonal projection onto the data manifold. And at high levels of noise, it's just pushing the samples inward toward the mean of the big Gaussian blob. And if we think about what's going on when we draw samples going left to right, we are first make a little noisy step using this vector field, then using this one, then using this one, and so on. And eventually projecting onto the data manifold and eventually moving close to the nearest data point. It's a 2D cat. Here, this same thing, a little more close up. Real cat, real images, same thing is going on. There are actually empirical studies, and also theoretical ones showing this, at the very high noise levels, there's a lot of mixing going on, and we just approach a Gaussian approximation to the data set. Near the middle ranges, you approximately project onto low dimensional manifold approximations of the data. And then at very low noise levels, at the final steps, you refine and go close to realistic data samples. All right, so that concludes the section on diffusion models as latent variable models and score-based models. So now let's talk about conditioning and guidance, which is important in many applications of diffusion models for Bayesian inference, and, well, really most places where they're practically deployed. Now, like any generative model that has neural networks involved, a diffusion model can be made conditional. Say if I want to generate not just pictures, but pictures given a caption, I just give the caption as an input to all the learned objects involved in my model. So if I have a data set of images together with captions, I just have to make the model I train, which approximates the conditional expectation of Z0 given Zn, take the caption as an input. So of course the model can be made conditional. So image given caption, what else? Image given class, anything you like. And this principle is also important, say, in diffusion for simulation-based inference, where I have an observation, and if I can simulate observation given, say, initial condition or latent, I just try to recover that latent given the simulated observation. But a more difficult question, which comes up in inference, is what if I have an existing diffusion model, P of x, which gives the models a distribution P of x, and I want to tilt it to sample a posterior distribution. Like, say I have a model of images, and I have a classifier which tells us if a given image is a 7, and I want to get conditional samples. Now that problem is much harder. Can we solve it? Well, yes, but under some conditions. This will be covered in 2 days, but just to give a brief answer, let's write Bayes rule. This is Bayes rule just with log. Let's take gradient with respect to Z, and I get the Bayes rule for score functions. So think of y as an observation and z as the object over which we're trying to perform inference. So the score of the posterior is the score of the prior. I have it here. The score of the posterior is the score of the prior plus the gradient of the likelihood. So because the predictor of Z0 given Zn in a diffusion model is the same thing as the score function, to know the score of the conditional distribution, the posterior, I need to know the unconditional score, which I have because I have a prior diffusion model. Okay. And I need to know the gradient of this likelihood function of classifiers. See, probability that a given image is a 7. But if you look closely, this classifier takes Zn as input, not Z0. So this has to be a classifier that's trained to accept noisy data, not Z0, but Zn. So if we have trained classifiers which tell us if a given noisy image for every level of noise is a 7, then we can just exactly, analytically get a diffusion model which samples 7s, only 7s. So it samples the posterior distribution. But tragically, and this is the biggest problem for diffusion models in Bayesian inference and inverse problems that we'll hear about in a few subsequent talks, if we only have classifiers that take noiseless data, so x, Z0 as input, then getting in analytic form the diffusion model which samples the posterior is intractable. So instead we have to resort to Monte Carlo techniques or amortization of various others that I will talk about on Wednesday. Right, so now let's pass to the continuous time perspective. I think the first slide of this section will summarize it pretty well. So I'll show that to you. So before we before we had a diffusion model as a deep hierarchical latent variable model, which had a sequence of a fixed number of variables where the transitions from each variable to the next were fixed Gaussians in one direction and Gaussians with learned mean in the other direction. So a picture like this. So here it's in 1D, I have the data over here, and I have possible noising trajectories right to left shown there. So what if I just increase the number of steps? And I get a picture like that. And then I take the number of steps to infinity, and I get something like that. So if you start on the right, that's at 0, and you go from right to left, you noise using the posterior distribution Q, you are following a Brownian motion, which starts at Z0 and is gradually adding Gaussian noises as you go right to left. And Brownian motion is actually a continuous time thing, which I've just happened to discretize with a fixed number of steps in these first two pictures. So what we'd like to do is to think of the generative process and diffusion model as an underlyingly continuous time thing, which we just happen to discretize because we can't simulate things in continuous time on the computer. So yes, in fact, everything I said before can be stated as just discretizations of a thing that's running in continuous time. Which, just for the purposes of drawing a sample, we discretize in time to generate samples in a finite number of steps. So this is what we'll examine in more detail next. So we're going to want to think of generating samples as something happening by running a continuous time dynamical system, which may be stochastic, as in the picture on the left, or deterministic, as this picture on the right. That's the final connection that I want to sketch for you. Right, so just a little connection. So it may be familiar, a common stochastic dynamical system used to sample a distribution is Langevin dynamics. So if I have a distribution, say with that density, it's a mixture of 3 Gaussians, and I have its score function, then I can draw samples from the distribution by making gradient steps in the score function and then adding appropriately scaled Gaussian noise. So that's the Langevin stochastic differential equation. And if stochastic differential equation is scary, then we can just think about how it's simulated in discrete time. So to step from xt to xt plus delta t, I make a step along the gradient scaled by delta t, and I add a noise of variance 1, which is supposed to be scaled by square root of delta t. And if you have seen a theory of stochastic differential equations, then you know why, and if you have not, then the scaling is necessary so that when you take the limit delta t to 0, this thing behaves as you like. So under basic assumptions on these densities, running this in continuous time will give samples that approach and limit the density p. So here, I run it, and eventually, or very quickly, the samples become distributed with the target density. So diffusion models, in fact, are actually amortized, annealed Langevin dynamic samplers. So let me explain that. So it turns out, so remember the Brownian motions that started at points z0, and went right to left? So this is a Brownian motion, which is described by the following very simple stochastic differential equation. If I have initial conditions, so z0, which is starting at the data set, then the marginal density is, as we saw, a mixture of Gaussians. And zt, now t is a continuous time variable, given z0, is Gaussian with mean z0 and variance t. There's a Brownian motion run for time t has variance t. Now, there are some identities in stochastic differential equations which tell you that you can write the same stochastic differential equation in reverse, now going left to right. And when you do that, you have to change the drift term, so the linear term in the differential equation. This is called Nelson's identity, but in diffusion papers it's often attributed to Anderson, even though Anderson published it about 10 years after Nelson, 1972 and 1960 something. So if I want to run this differential equation in reverse, I have to make steps on the score of the marginal density and add a small amount of Gaussian noise. So, just to see on the picture, if I want to simulate this same stochastic process right from left to right and right to left, I have to use different coefficients of delta t. Now, the way I generated this picture is by starting at a data set with 3 points blue, green, red, and just having no drift term, just adding Gaussian noises right to left, Brownian motions. So I was following this on the right, this vector field. So I start here, I move along the vector field, add a bit of Gaussian noise. Move along the vector field, add a Gaussian noise. But if I want to simulate this left to right, I should follow this other vector field, which is shown in the middle picture. So I start the point on the left, I follow the vector field, I add a little Gaussian noise. And in order to end up at the 3 target points, my vector field better point at them, especially when the time is small, so I'm close to the right edge. So this should convince you that I need to change the drift when I reverse the time. And the correct way to do that is to add this term, which is the score of the marginal density. So same thing happens for high-dimensional data, as in the 1D example I showed before. So because fitting a diffusion model as we saw it earlier is the same as learning the score of the noise data, and learning the score of the noise data is the same as learning this drift term of the reversed stochastic differential equation, which allows us to simulate left to right. When we fit this denoiser, the expectation of x0 z0 given zn, we effectively learn the drift of this stochastic differential equation, which can run in reverse time from left to right in the previous picture. Except the only difference is the time, or the noise level, now becomes a continuous variable. Not just fixed number of steps, different levels of noise, but something which can vary continuously. Now that the time can vary continuously, I could train this model simultaneously for all values of the noise, for all values of variance added up to the largest I care about, and sample it with varying numbers of steps, however many I like. And each step is just taking a step on the gradient of the log marginal density and adding a bit of noise. So just like the step in Langevin dynamics. Just the target density is evolving from very noisy to just the data distribution. Now, the choice of how many steps I use to sample after I've trained the model can affect the results I get. So here's that same distribution with 3 points, mixture of three deltas. If I sample with very many steps, I get something very close to those continuous time pictures I showed before. In fact, that's how I made the continuous time pictures I showed before. I just took delta t to be tiny. But if I use very few steps, I'll get very noisy results. Because of course, for example, if I made my step say 1/10, on the last step, a Gaussian noise of variance 1/10 is added. So there's no way I can always land at one of the three target points. So the more steps I take, the finer I discretize the integration of the stochastic dynamical system that I fit, the better result I get. And this is an important choice at inference time. It allows us to trade off sample quality for compute. The same happens with large image generative models. Here's images generated with the same random seed. That's why they're so similar. Here's a cat, here's a bear, just with different numbers of steps used for integrating the continuous time stochastic dynamical system. So few steps, blurry image, many steps, realistic image. A big direction of ongoing work in diffusion models is how to fit ones that can be that can be sampled in fewer integration steps. And for instance, there is work on distillation where you try to learn an amortized integrator, which predicts the result of integrating the ODE or SDE for a certain time interval and get away that way with fewer sampling steps. Right, now we'll conclude with one more connection, continuous time, which is important for a couple of reasons. So this is the general form of the Nelson's identity from before. If I have a SDE of this form, so dx equals drift plus diffusion rate. So before just dx equals dw, that's a Brownian motion. The reverse SDE has this form. We have to add an extra term involving the score of the marginal density. Now it turns out there's also ordinary differential equations, so a deterministic dynamical system, which generates the same marginal densities when integrated in continuous time. And for that one, we'd have to just average these two stochastic differential equation drifts. Now this looks like magic facts, so let me just show a picture. So in the middle, we have the stochastic dynamics, which I showed before. On the left, we have trajectories coming from integrating the ordinary differential equation given by that formula. And on the right, we have the marginal densities. So trajectories both from the ODE on the left and the stochastic system in the middle are following the marginal density shown here, which at every time step are a mixture of Gaussians centered at the 3 data points. Now, why are we interested in ordinary differential equations rather than stochastic ones? Well, ODEs can generally be integrated with less error, even though they're more sensitive to errors of approximation at high noise levels. In addition, they can give us better likelihood estimates because we have a deterministic mapping from point on the left to data sample, and thus we can compute the change of density factor and get direct log likelihood estimates from a diffusion model, while with the latent variable view, we can only get variational bands. Here's another picture mapping between two data sets. Here is 8 Gaussians and then two semi-moons, two moons. The picture on the left, the picture on the right. On the left we have ODE, on the right an SDE. They're passing through the same marginal densities. Okay, let me conclude on this. We're perfect on time. So what to remember from this short introduction to diffusion? Diffusion models are, at least their widespread adoption and the impressive results they've shown are a powerful tool for approximating multimodal distributions in high-dimensional spaces. And they can be understood from different points of view, as score-based models, as latent variable models, as continuous time stochastic processes with parametric dynamics. And there's a growing scope of applications for them, just beyond the kind of simple Euclidean data given a finite data set that I've shown today. What did we not talk about? Well, we did not talk about how to use diffusion models for discrete data, for data on manifolds, and for non-Gaussian transition kernels and so on, but do know that these generalizations exist. We haven't talked about diffusion models without noise. And here I mean two things. First of all, I showed you the probability flow ODE, the ordinary differential equation, which generates the same marginal densities as the diffusion model. But there are ways of training these deterministic dynamical systems, which are sometimes more efficient, which don't assume an underlying stochastic system. It's called flow matching. There's a lot of recent literature on that. Also, Schrödinger bridges, where there is no noise in the intermediate steps, but there's no initial noise. So mapping between two distributions by a stochastic dynamical system. And I also haven't told you about diffusion models without data, but that will be the subject of Wednesday's presentation. So we talked about how to train diffusion models given a data set, which was easy. We take the data set, we noise the points, we try to predict the original data. But what if instead we can only query for the density of the distribution we want to sample, but we don't have unbiased samples from it that we can use to maximize likelihood? And that will be the subject of my Wednesday talk, and I think others on Wednesday and Thursday. Right, I think I stop here with 5 minutes for questions.
Any questions? Please go ahead.
Please.
Thank you very much. It was a great talk. It's really inspiring. What's some point you say that if we go for non-Euclidean data, we lose some property, and of course, Gaussian noise.
Yeah.
It's no more relevant. Can you say a little bit more about, different ways to tackle non-Euclidean data?
Different ways to
tackle non-Euclidean data?
Oh, yes. The two properties we might lose are simulation-free training, meaning that we get Zn directly from Z0 without simulating the whole chain. The second is the lower variance learning objective, where we can predict Z0 from Zn rather than Zn-1 from Zn. In discrete spaces, similar properties exist. In discrete spaces, for example, used for text, the noising process may not add Gaussian noise, but randomly replace words by a mask token or by other words, other tokens. And there you actually have similar properties, so everything's simple. If you're on a manifold, there's really no escape. So unless you have a tractable form for the heat kernel, like simple analytic form for the heat kernel, there's not very much you can do.
Thank you very much.
I was wondering about guarantees for sample efficiency for diffusion models. Are you aware of any?
Yeah, I am aware they exist, but I couldn't. I could point you to some surveys.
Okay,
So in the SDE case, you have additive noise.
Yes.
So then you start with a noise to Gaussian, and then you revert. So if your sample is coming from a distribution that has heavier tails than Gaussian.
Yes. I mean, for example, ones that don't even have finite variance. Right, so the correctness of the SDE reversal generally requires finite variance, for example. But there are generalizations of diffusion for heavy tail distributions, for example, using Laplace transitions rather than Gaussian. So that's been explored.
So you presented multiple perspectives on the diffusion models. I think for the VAE or latent variable perspective, you pointed out a couple of advantages. For example, that we are in a probabilistic framework, so we can have work in lower dimensions, etc. For the continuous time formulation, what would you say are the advantages over than the probabilistic kind of or latent variable perspective?
I mean, from a mathematician's point of view, you can say the continuous time things are always nicer because there's a associated partial differential equation which allows you to analyze the evolution of density. In discrete time, you get just a sequence of intractable integrals, which is harder to deal with. And another advantage of continuous time is it allows us to vary the discretization. So if we're just sticking with the latent variable model, we can't just replace it with another latent variable model with a different set of latents. Maybe take two co-prime numbers and have one with p steps, one with q steps, and you're in trouble because no shared variables anymore. In continuous time, it's so simple. You've just chosen different discretization.
I guess the shortcut where we go from Zn from Z0 to Zn, where we connected them together in a way, we could think that's a bit where you bypass multiple time steps, right? So you could actually have started with a very large n, but it doesn't matter in a way because you're bypassing many of them anyway.
Yes.
So from that perspective, are there just algorithmic kind of advantages that you can tap into the literature on how to efficiently solve ODEs and SDEs? Is that from a applied perspective a main advantage?
So if I understood your question correctly, you're asking, does the continuous time perspective allow us to take advantage of numerical analysis related to ODEs and SDEs?
For example, or as a computational tools.
Yes, great. So there is lots of work on that. It's also, I suppose, related to the work on sample efficiency and on approximation guarantees. So when you're solving the SDE or ODE, nobody forces you to use the Euler or Euler-Mariano stepping scheme. You can use better integrators, and that way get better samples in fewer steps. And you can even use learned integrators, distillation or partially amortized solver for a trained diffusion model. Any questions for last 10 seconds?
If not, let's thank the speaker.